6.1 Introduction to Exponential and Logarithmic Functions. Number 1, Graphing Exponential Functions. So first, by definition, an exponential function looks like a to a power x, where a is a real number, positive, and not equal to 1. We call it the base. If it's equal to 1, then we have 1 to the x, which is a constant. So, example, y equals 2 to the x. Want to graph it. The base is 2, so if we make a table for x and y and give anything for x, so if x is 0, 2 to the 0 is 1, if x is 1, 2 to the 1 is 2, if x is 2, 2 squared is 4, and let's give some negative because x can be negative or positive, all real numbers is the domain, so 2 to the negative 1 is 1/2. So the graph will look like this. So I have 0.01, I have 1, 2, right here, 2, 4 goes on, and negative 1, 1/2. So the graph is a curve, looks like this. So we see as x goes to infinity, as x approaches infinity really big, y is also approaching infinity, goes to infinity. As x is approaching negative infinity, x is really small, negative number, y is approaching 0. So here the base was 2. Now we're going to see what the graph looks like if the base is 1/2. So 1/2 to the power x, which is 1/2 to the x. The base is 1/2, which is less than 1. So when we make a table here, x is 0 and 1/2 to the 0, that would be 1. If x is 1, we have 1/2. If x is 2, 1/4. And now negative number, if x is negative 1, 1/2 to the negative 1, that is 2. If x is negative 2, you get 4, and so on. Graph these points. It goes through 0, 1 again. 1, 1/2 would be here, and so negative 1 would be here, and this is what the graph looks like. So we notice it's decreasing when the base is less than 1. So some properties. Properties of the exponential function. If the base is, for example, 3 or 4 or 5, the graph will be very similar to the graph 2 to the x. If the base is 1/3, 1/4 will be similar to the second example. So for our function a to the x, where a is positive, not equal to 1, we call it base, we see this function is continuous. It has no holes, it has no jumps. It's also 1-to-1. It passes the horizontal line test, and the domain, in both cases, is all real numbers. The range, in both cases, the y values, is from 0 to infinity. We see that it's increasing in the first case, when the base was 2, or if a is any number greater than 1, and it's decreasing in the second case, if the base, remember, but the base has to be positive, so from 0 to 1. We have horizontal asymptote in both cases, and that is the x-axis. In both cases, we have y-intercept 0, 1. Both graph goes to that point, 0, 1. So example, graph f of x equals 2 to the power x minus 2. So this graph will be similar to the parent function. So the parent is y equals 2 to the x, but it's going to be 2 units to the right. So a rough sketch. The base is 2, so it's increasing This is the parent function, y equals 2 to the x. If we're going to go 2 units to the right, then we're going to go through that point. Still going to have the same x-intercept, so this is our graph. 2 units to the right. This is x, and this is y. Now, the base of the exponential function can be any number that's positive, but what's interesting to see when the base is the constant e. So number 2, we'll talk about the number e. The number e, which is Euler's number, and it's approximately 2.71 and so on. So the graph is very similar to the graph 2 to the x. Still going to go through that point. So this is the graph of the exponential function with the base e. Calculate, using a calculator, what is the value of e to the 3? So find the constant e on your calculator. Approximately, it's going to be 20.0855. E to the 0, you don't need a calculator. Any number to the 0 power is 1. E to the 1 is e. So now the logarithmic function is actually the inverse of the exponential. So number 3, let's talk about the graph of logarithmic function. And before that, let's see where the logarithmic function comes from. So the exponential function y equals 2 to the x. If we switch x and y, if we want to find the inverse, it's by switching x and y, so x equals 2 to the y. And then to solve for y, we actually cannot do that with the operations we know, so we need to come up with a new symbol called logarithm. So y is equal to logarithm of x base 2. And we know that the function and its inverse are symmetric with respect to a line y equals x. So if I already know the graph of 2 to the x right here, this is y equals 2 to the x, the exponential, then the graph symmetrical to it with the line y equals x, or we can make a table for that and graph it. It's going to look like this. So this is y equals log of x base 2. So definition, logarithmic function, base a. Y equals log of x base a. X is positive, a is positive, not equal to 1. We call it the base. It's still the same base. And we saw what the graph looked like. Properties of y equals log of x base a greater than 1. So if the base is greater than 1, we have a continuous function. It's 1 to 1. It passes the horizontal line test. It has a domain. Let's look at the domain, the blue line. It's from 0 to infinity, and it has a range that's all real numbers. Since a logarithmic function is the inverse of the exponential, when you switch the domain and range, from the exponential you get domain and range for the logarithmic function. So the exponential function had horizontal asymptote. The log function has vertical asymptote. And that vertical asymptote is x equals 0 or the y-axis. So finding some certain logarithms. That will be number 4. Finding certain logarithms without a calculator. So logarithm of 10,000 base 10. If the base is 10, we often don't write it, but I'll write it down. So what we want here is a power such that 10 to that power is 10,000. Well, 10,000 is 10 to the 4th, so that power is 4. And that's what the logarithm is equal to. Now, logarithm of 3 base 9. So we want 9 to a certain power to equals to 3. That is 1/2. We know 9 to the 1/2 is square root of 9, which is 3. So that's 1/2. Log of 1 base 6. So we want 6 to some power to equal to 1. Any number to the 0 power is 1. We know that, so this is 0. Log of 8 base 8. That's easy. 8 to what power is 8? Well, of course, 1. And a log of 8 base 2. 2 to the what power is 8? We know that's 3, and that's what the logarithm is equal to. So we can derive some formulas here from what we observe. If we have a logarithm of 1, and doesn't matter what the base is, could be a, we know a to a 0 power is 1, so this is equal to 0. So log of 1, any base, is equal to 0. Another formula is if the base is a and we're taking logarithm of a, then that's always 1, because a to the 1 power is a. So converting between exponential and log function. Converting between exponential and log function. Since they're inverses of each other, it's very important to go back and forth. Log of x base a is equal to y is equivalent to a, same base to a power y, equals to x. So this is very important conversion formula. So example, write as log equation. So you're given exponential equation 16 equals 2 to the x. This is an exponential equation because x is an exponent, and we can write it as a log equation. Write the log, the base is the same, 2. So 16 is what logarithm is of. So it's 2 to a power x equals 16. Another example, that's A, this is B, e to a power t equals 70. So if the base is e, we use natural log ln instead of log base e, and we don't write the base, we know it's e, so t goes here and 70 goes here. Ln of 70 equals t. Now the opposite, if we want to convert to exponential equation, convert to exponential equation using the same formulas, but now they give you a log equation. A log of 32 base 2 equals 5. How do we write this as an exponential? Start with the base, to the power equals 32. And log of q base a equals 8. So we can write as exponential. A to a power 8 equals q. Finding logarithm using a calculator. So example, let's calculate log of 645,778. So if the base is 10. We sometimes don't write it down. That's what the calculator has, base 10. So that is 5.8101. Okay, now calculate log of -3. If you type this on your calculator, it's going to say error does not exist. It's not possible because remember the domain of the log function was the blue graph, only the positive, x greater than 0. Natural logarithms. So natural logarithms are logarithms with the base a, base e. So for example, ln of 645,778, find the ln key on your calculator, and that's approximately 13.3782. So natural logarithm of 1 is still 0 because e to the power 0 is 1, and natural logarithm of e is still 1 because e to the power of 1 is e. And finally, change of base, changing bases. So the basis we have on the calculator is base 10, which is the common logarithm, and base e, the natural log. So we can change to any base we want using that formula. If I have logarithm of m base b, I want to change the base to base a, then that's log of m base a divided by log of b base a. Example, that's a very important formula for changing bases. Example, find logarithm of 8 base 5. The calculator does not have base 5, so we need to convert either to base 10, so that's log of 8 divided by log of 5, or use natural logarithm. So either this, or you can do ln 8 over ln 5, doesn't matter, you'll get the same answer. So approximate 1.2920. 1.2920. And that concludes this lecture.